So today what I want to talk about is strategies in peptide synthesis. And it's going to spend quite a bit of time talking about solid phase peptide synthesis. That's why I'm titling the lecture. But we're going to be talking about convergent versus divergent syntheses and some of the challenges in this kind of work. I'm just going to get my textbook open. There we go. Okay. The right page. So let's think about a peptide. I don't know, something relatively simple. Okay, so I know what Kirsten's favorite amino acid is, and I know what Paul's favorite amino acid is. So, Ashley, what's your favorite amino acid? Or Susanna? I'm going to get it from both of you.
Serine?
Serine? Okay, I like serine. Ashley, do you have a favorite amino acid? Is Ashley there? Okay, Ashley doesn't get a choice then. Ashley's favorite amino acid is going to be leucine. Because I really don't like histidine. I'm just going down her alphabet, and there's no... Oh, we haven't done alanine. No one's favorite amino acid has been alanine. Okay. So let's say we had a sequence. Okay, so there's a peptide. So, again, coming back to this idea that let's say we're going to do solution phase synthesis. No one in their right mind would do solution phase synthesis of this, but you could. So what do I mean by solution phase synthesis? I mean that the synthesis does not take place on a solid support. It's like normal chemistry where you mix the chemicals together in a flask, you mix them all together, everything's soluble, which is the whole solution phase thing. And at the end of that, you need to isolate your amino acid and peptides from everything else that's in the mixture. But there are some benefits to solution phase synthesis for some couplings, and they just never outweigh the costs. But let's say we're doing this, and we know that every step is 95% yield. That's not true. Most of the steps are going to be higher than 95%, and some of them are going to be quite a bit lower for no particular reason because amino acids hate you. This coupling, for example, is going to be a nightmare. Everything else is going to be fine. But tryptophan and proline together are just a pain in the ass. But we'll say 95% yield every step. We are going to, I think, in one of the assignments, I ask you to take a look at some of the side chain protecting groups that get used for all these standard amino acids. So I'm not going to go through that in the class. Conveniently, they're all in the book I sent. And I'm going to share another book with everybody because I shared it with Paul because he asked. And it was about, it's all about carbohydrate stuff. It's called Glycoscience. It's 6,000 pages or something. Everything you need to know about sugars. And it's like $4,000. So I'll share an version, and it's not going to cost you $4,000. So 95% yield every step, and we're going to use FMOC protection. So if you remember from last class, that means our building blocks I did not get into. I talked about epimerization with the oxazolinone. Okay, we'll talk about that today. I don't know, alanine. Okay. So this is where we've got this. Now, there's multiple ways we can do this synthesis. One is, well, what we want to do basically is minimize the total number of steps that your full peptide undergoes, because each one of those is only 95%. So the most straightforward way to do this is build this the way that we would build any normal amino acid. So, or any kind of normal protein in solution. So what I'd probably do is I would start with proline. And I would protect the C-terminus. No, let's use T-butyl. And on my N-terminus, I would have my FMOC, because that's what I buy. And I would deprotect the FMOC. Why? Because I need a free NH2. Okay, so I've got that. So I'm starting over here with the proline. Then I couple by adding FMOC tryptophan. So again, this notation means FMOC on the nitrogen, the amino acid is tryptophan, the carboxylic acid is free, OH. Normally, this tryptophan will often be protected on the nitrogen of the benzimidazole of tryptophan, but it doesn't necessarily need to be. Tryptophan is the one you can get away with not protecting it because that benzimidazole is not all that reactive. Anyways, so we do that, and we toss in some coupling agent. We're just going to use the same coupling agent for every one of these, HCTU, DIPA. And this is all done in DMF, a solvent. So we mix those together, and what we'll have then is we'll have proline, CO2 T-butyl, bound to tryptophan, FMOC. That was step 2. Step 3 is deprotect. That will give us tryptophan, proline, CO2 T-butyl. I'm going to start a new page, and H2. Step 4 would be to couple phenylalanine with a free carboxylic acid and an FMOC on it. So you see at each point, we're introducing the new amino acid. It's got the free carboxylic acid, can react with the free amine on our peptide, and it has its amine protected with an FMOC. So what that's going to give us on a new slide is proline, tryptophan, phenylalanine. And now the problem with my theory of a new page is that I can't remember what the fuck my structure was. So, just going to skip back for a second. Psi. So step 5 is a deprotect. NH2, F, W, P, CO2 T-butyl. Step 6 and 7 adds isoleucine and deprotects it. So then we're going to have NH2 then I can add in Ashley's favorite amino acid, although we have no evidence of that. And again, and then we're going to deprotect it. So we add it, we deprotect. And then we're almost home. Okay, so for serine, I'm going to write TRT, which stands for trityl, and that's in the assignment. And trityl is a protecting group for a side chain. It's really acid labile. It just falls off when you look at it wrong. It falls off in lemon juice. It's really, really acid labile. Anyways, it's on the side same of serine just to protect that, so the OH of serine doesn't do something funky. It's kind of funny. It never is going to do something funky, but we all buy them protected because we're superstitious. And it looks like a nucleophile, and I'm worried about being a nucleophile when I'm not looking. Then there's one final step, and that is our global deprotection, where we need to wipe out both the trityl group and the T-butyl group. And those are acid sensitive. So at no point in this entire synthesis have we used acid. We actually haven't really done anything except couple with weak base, DIPA and HCTU, and deprotect. Going back to last class's lecture, this is 20% piperidine in DMF. It's a lot of a secondary amine that takes off the FMOC. So step 12 is strong acid, trifluoroacetic acid, just in case. That's what TFA is. And then we have our final product. Okay, so we did 12 steps. That last step did two things, right? It took off two different protecting groups, so we'll give it that 95%. So the overall yield is 0.95 to the 12. With my handy little calculator. No. It's 54%. So 54% yield to make something with only 5 amino acids on it isn't great. So first of all, 95% yield sounds like a really good number. As a synthetic chemist, I'm overjoyed when I see that value. As a peptide chemist, I'm dispirited and crushed because my yields are going to plummet. 54% is, well, basically it's shit. But That's pretty typical. So is there a way we can shorten this synthesis? And the answer is yeah, there is. We can do a, so I'm just going to still write it up here, just the sequence. And I forget what the rest of it was. WP. We can build it in parts. Because what we did here is this poor proline was carried through every single step of that synthesis. So what if we don't do that? What if instead of what we did, we do a convergent synthesis? So anyone who's taken classes in sort of synthetic methodology might come across this term, convergent and divergent syntheses. And the idea of a convergent synthesis is that you make two parts and you stick them together. Divergent is when you make one part and then you branch it off and to make lots of different things. But a convergent is often more efficient because no one piece is going through all of the steps. So if what we do instead is we make two different it's not massively efficient when you only have 6,5 amino acids, but let's say we aim to make these two, one tripeptide and one dipeptide. That's even messy for me. Well, this one, using a retrosynthesis arrow, comes from S CO2H FMOC N plus AI and H2 and of course AI comes from so if we count this isoleucine and we look, okay, so it needs to get to here, it needs to do two reactions because we need to deprotect the FMOC and we need to couple. So for the isoleucine, our step count is 2 to here. And then we need to deprotect this FMOC. I've deprotected that, so right, 3 steps. And then as coupling, that gets us to here. So here it's 4 steps from the starting material to this tripeptide. There's a deprotection, a coupling, a deprotection, which gets us this guy, then a coupling, which gets us this guy. That isoleucine is going to go through more steps than anything else here. You're going to have a very similar process to make this tryptophan proline linkage. You'll start with this one you can actually start with a deprotected one and a protected one. But it's not going to be more steps than 4. Then to bring this isoleucine to the final product, It needs to do one more deprotection to remove that terp-butyl group. No problem, strong acid. Then a coupling with our newly deprotected tryptophan. And in a final global deprotection where we take everything off. So it's got 3 more steps. So I guess 7 total steps from the isoleucine building block. So what we call this is 7 is our longest linear sequence. So it's the most steps anything has to go. So if, again, we're still in this 95% yield, we can really calculate the yield based on that isoleucine starting material. And that's gone through a longer step than anything else. So now we do 7 95 to the 7. Don't hit the negative sign. We're at 70% yield. So what we've done is we managed to increase the yield because we've decreased the total number of steps that any one piece needs to go through. And again, that's because that poor proline in that previous reaction needed to be carried through every single reaction that peptide did. Whereas this one, the isoleucine can avoid everything except, basically it can avoid the whole tryptophan tryptophan proline coupling and putting them together and getting them all deprotected and set up and stuff. The isoleucine could avoid that mess. And so it goes through fewer steps. And so your yield's going to be higher. But all these are really kind of awkward ways to do that because each of those times you're going to need to, basically run a column on this thing and purify it in between each step. And that's a pain in the ass. So this comes down to the whole solid phase peptide synthesis. Or SPPS. So what you have is basically take some polystyrene, you take some acrylate, you heat them, a bit of AIBN, and you get a mess. But turns into a solid bead because this stuff all cross-links each other. Often there's another cross-linking agent in there. The one that gets used a lot for this, just trace them out, not very much of this because you don't need much to cross-link, is this guy. This does not matter at all. I really don't care about this. But I don't know, I'm just... Maybe someday you'll need to make your own solid phase peptide beads after the apocalypse. Don't know why we want to make peptides, and I don't know where you're going to get your DMF from, but it's a weird world. So you have these beads. Single molecule, insoluble. And depending on what the bead is, a lot of them will have OHs on their surface, and they're kind of designed for that. It comes from a reduction of that methacrylate after you make the bead. And now what we need to think is, how do we attach things to this bead, peptide? So this comes to something that's actually pretty near and dear and close to my heart, which is self-immolative linkers. So the most common thing out there is something called Wang resin. I think we briefly touched on this last class. And what that is, you got the bead, we have our alcohol, and it's then attached to this. Okay, cool. Don't quite see the point. What's closer to the bead? Well, it's a mix of different things, but often what we have is a diphenyl group here. Okay, still don't necessarily see the point. So what we're going to do now is we're going to take that bead and we're going to react it with an amino acid. And we're going to react it not with the amino acid itself, just want to make sure I do this right. So let's say we have glycine. Yeah, no, this is good. So we need to find a way to react. I just confused myself for a second. I'm sorry. So what's going to happen here is this isn't going to really do anything. We can turn this into the acid chloride. That works okay. What works more often is you turn this into the anhydride. I'm going to protect the nitrogen. I've never actually done this. I always buy my beads preloaded because I'm not an animal. This is actually really difficult to do. The chemistry is kind of shit, and you never know how much of this stuff goes on. So this is an anhydride. We've seen lots of anhydrides. That's not a surprise. You take the alcohol with an anhydride. We add a base. This is where it gets tricky. You need to make sure you're using the right base. You don't want to decompose your Wang resin. You don't want to react with your anhydride. Common base for this is terbutoxide. Strong base, non-nucleophilic, so it's not going to touch your FMOC. It's going to fully deprotonate your alcohol. It's non-nucleophilic, so it's not going to do anything weird with your anhydride because it's non-nucleophilic. So if we do all that, hopefully fall for the cleavage of the anhydride. And we're going to end up with a bead Phenyl. O. Okay. So what we've done now is we've actually attached an amino acid. And now what we essentially have is we have that NHF mock, and we can now go through and do chemistry. So I'm going to just treat all of this piece here and call this the green bead. And we'll continue with that. And we're going to come back afterwards to talk about how to deprotect this. The mechanism of that. So let's say we have our green bead. It's got alanine with an NHF mock attached. Now you'll have a whole bunch of these on the bead. Normally, the way we talk, because it's really hard. Normally, when you have a chemical, you weigh it, and then you get out your calculator, and you know the molecular structure, and you can determine the number of moles because it's the weight and all this. For the beads, what we normally use is loading, and that's always measured normally in millimoles per gram. So a pretty standard loading is between, like a low loading is about 0.1 millimoles per gram of resin. And it'll go up to about a high loading is about 0.5 millimoles per gram of resin. You can go much higher, you can go much, much lower, and we'll talk about why you want to go lower and why you want to go higher in a bit. Moles refer to functional groups. On surface. So I've drawn this on the surface, but that's not really an accurate way to think about these. These are more like, cave networks. The bead is this polymeric, roughly spherical thing, but it's really porous. It's got holes all the way through it, and it's kind of a mess. And so the peptides can be growing in the holes inside the bead or on the surface of the bead. So it's not uniform in any way. Okay. I was just suddenly thinking about Pepsi, and I completely lost my train of thought. So we have this amount of this resin stuff. We have our stuff on a resin. And now we want to put our amino acid on there. Now, when we're doing solution phase, we can live with 95% because we can purify after every step. But on solid phase, we can't. What do I mean by that? Well, let's think about what happens. So, I got a bead. It has alanine, an F mark on it. And I treat that with 20% piperidine because I'm going to remove the F mark. And now I've got a bead. Alanine with an H2. Okay, whatever. The thing is, I can't separate the beads from other beads, right? Like I'm kind of stuck. There's multiple copies of this thing all attached to the bead. So I need this to be otherwise I'm going to generate impurities really, really fast because every impurity always stays with me. I can't remove them because they are on the bead. So I need all my reagents to be really, really good. So how do I do that with the coupling? This is normally not unusual. this kind of yield. Deep protections normally go completely pure. The wonderful thing is that when I'm done this reaction, I just filter, because my peptide, my product, it's not really a peptide now, it's like one amino acid, but it's attached to the solid thing, and that's just not going to go through like a glass frit. Whereas all that piperidine and DMF, all the crappy FMOX shit that I just took off, little pieces of hair, whatever, I can remove that through filtration. You'll probably catch the hair with your filtration, but you can actually physically go and I guess remove the hair. So our next step is we're going to take 5 equivalents of our next amino acid. Which we're just going to say is serine. I think we're just going to rework our sequence a little bit here because I don't remember what it was. Doesn't really matter. We're going to take 5 equivalents of our FMOC serine. We're going to take a slight excess of our coupling agent and a generous excess of base. So again, technically, we need 2 equivalents of base to do a peptide coupling, because we are going to remove a hydrogen here, like an OH, and a hydrogen off this nitrogen to make this all work and generate an equivalent of water. But we always add a little bit of extra just to help this guy out. Because you're not actually generating water, so that you're not sort of trading that hydrogen like you normally are when you're making these kind of condensation bonds. But because you have such an excess of that guy, it's going to work really well. And yeah, it works well. It's about 99%. And I'm going to say that's not good enough. Because again, let's say we need, like, even with just 5 amino acids and 95%, our yield went down to 54% on each step. So 99% sounds great, but it's not good enough. Because especially if, let's say we want to make a 30 amino acid peptide. So if we just quickly go in that and sort of say, okay, 30 amino acids, every step is 99%. There's 2 steps per amino acid. So I've got 0.99 to the 30. That's 74%. It's actually not bad. 30 amino acids to the 60. 55%. So I don't know if you can see it. You probably can't. Doesn't matter. There we go. For posterity. Not bad, but it's kind of making a good assumption that everything's 99%. So if this is not good enough, how do we drive that yield up? Well, we do it again. We don't deprotect. What we do is any little bit of this guy is now reacting. So, but instead of this being 5 equivalents, I just reacted 99% of it. So now it's like 500 equivalents compared to the tiny little bit that's left unreacted. That will react. You're adding plenty. You're going to push it all away. So we'll probably do another 99%. Overall, about 99.95%. Now, we don't expect any weird side reactions going on, which are the things that are going to decrease our yields for some of these things. This isn't a particularly challenging coupling. Sometimes 2 amino acids just don't fit well. Remember, in I think the previous one I highlighted that there was this tryptophan serine issue that I was a little bit, or proline issue I was a little bit worried about. That's beyond the scope of the course, trying to figure out which amino acids are particularly tricky. The answer is arginine. Arginine's a pain in the ass, but tryptophan's up there too. So cysteine. Actually, a lot of them are really annoying. And of course, I'm working with tryptophan and cysteine all the time. So we can really drive up our yield by doing this. This is called double coupling. It's really wasteful. I just use 10 equivalents of an expensive amino acid. Like, it costs money, but trying to purify a 54% versus a 90% final peptide, you're going to spend all that money back and waste a lot of solvent and use a lot of reagents and everything and pay more energy to that final purification. So it is more environmentally friendly and economically viable to actually do these double couplings, even though it feels like, man, I'm using 500 equivalents of a reagent in that second step, which is a lot. It's still the better way of doing this. So we've extended our chain by one thing. And again, you wouldn't want to use 5 equivalents of amino acid in solution phase because it would be a pain in the ass to separate that. You would lose stuff on the yield on that. But again, the solid phase is no problem at all because at the end of the reaction, you just filter and you wash it a few times. And it's all gone. And you're ready to go. So the advantage of this stuff is you just wash it every time. By washing, you basically mix it with the solvent. And there are a couple of ways to do that. Just a sidebar, you don't normally want to stir these things. So normally when I say mix and I'm an organic chemist, I think, okay, grab my magnetic stir bar, throw it on, and mix. Problem is that pulverizes your bead because magnetic stir bars are made of iron and Teflon, and beads are made of soft, squishy polymer. And so they get destroyed. So that's not a good approach. So normally the mixing is either agitation, so, basically doing this with the flask. There's multiple solutions to that thing. You can hire somebody off the street to stand there for 24 hours doing this, or you can get like a rocker, or in our case, we have a robot that does that for us. The other thing that you often see is you bubble gas through it, and the gas just kind of creates little bubbles and everything kind of bounces around because of gas bubbles. And so those are both ways of agitating it and just making sure that all the solvent's moving around everything and everything's mixing. Anyways. Take 20% preparity in DMF, and we deprotect. So we've gone through the entire cycle now. There's not really a lot more to it, to be honest. You just go through this cycle again and again and again. What I'm going to talk about is something, a specific problem that can come up. So let's say we're coupling on a non-natural amino acid. We're going to call this amino acid Z. This is one of the layers that isn't used by a natural amino acid. And it's I don't know. Protect that as a trityl group. It's this guy. So compared to serine, this is kind of a serine analog in a certain way. Is Z going to be easier to couple or harder to couple, you think? And I'm going to go grab Pepsi while people think about that. Because I'm falling asleep. I'm sure you are too. See, we can't rely on Sam or Paul to jump in and answer this question because they're not here. And I'm not convinced that Ashley's here either. She could convince me otherwise. What do you think, Susanna?
Sorry, you asked if it's either easier or harder.
Harder to couple. If you had to make the peptide bond between this NH2, this carboxylic acid, or this NH2 and this carboxylic acid, which would you prefer to be trying to make? I promise you this isn't a trick question.
The S.
Why? Yeah, I agree with you.
I was thinking of like sterics.
Yep. Yeah, exactly. That's all it is.
Okay.
So that's why that's why tryptophan's such a pain in the ass, because of sterics. You just got that benzimidazole right there, and it's big. Sterics is the most important thing for defining these, because in general, the electron, like, there's two things. There's sterics and electronics. You're looking at these. This is the reactive center kind of thing here. It's all about the same. Like, there's alkyl groups. There's nothing really electron donating or really electron withdrawing that's right next to them. Like, the FMOC is here on both of them, but those cancel each other out. Alkyl groups. It's just sterics. This is quaternary. This is tertiary. And so this is going to be much... Okay, technically it's tertiary because it's attached to a nitrogen, not 4 carbons, but it's sterically quaternary. It's got lots of big shit around it. So Z is going to be a shitty coupling. So if we had to put on Z, good job. Thank you for answering that. Then we could do a few things to try and improve the coupling. One is we can go back to that list of coupling agents we covered and go, well, let's find a more active coupling agent. And I think there's tons of them. But the one I said that was super active was, let's switch HCTU for HATU. I didn't talk about why HATU is so active, so I'll do that now. But let's just draw the product first. Z can be whatever you want. You can define it any time you like. Like whenever you're making up one-letter abbreviations for amino acids, X and Z get used a lot, and then somebody will say, hey, this is what X is and this is what Z is. Sometimes if they have a lot of them, they'll use subscripts. They'll go like X1 through X30. I don't like that. I start using Greek letters because it's still one letter and they're kind of distinct. I find the subscripts get confusing because then you can't remember which X is which, and they all look the same. But you can do whatever the fuck you want. Anyway, so we're using a more active agent. We're doing this. I'm even going to say after double coupling, I would guess we're probably at about 94% yield compared to 99.5. Well, that's not great because now I've got this impurity, which is this free NH2 up here, which is missing Z. And let's say it's a long peptide. I need to keep making the peptide. Let's say it's 30 amino acids long. Approximately 94% of my stuff from this is going to have all 30 amino acids, but 6% is going to have 29 amino acids. We're going to be missing Z. But it'll keep adding the other one because it still has an active NH2. So when I try and add when I deprotect this and try and add my next amino acid, ASZNH2 and ASNH2 are both going to react. And actually, your ASNH2 is going to react completely because it doesn't have all that steric shit around it that the ASZ does. So you're probably actually going to enrich a little bit more than 6% in that guy. So that's a problem because that's going to make it a nightmare to separate them. Because it's a pain in the ass to separate 29 amino acid peptides from 30 amino acid peptides. They're basically the same size. Yes, one amino acid is different, but how much does that change the polarity of the molecule as a whole? I guess it could, but this isn't a really super polar amino acid, so it probably isn't. It's not like we're going to add charge to the whole thing. So that's kind of a nightmare. So how do we avoid this? We do what's called capping. So it's for exactly what I just said there. It's for when you think you might have unreacted H2. And it's pretty simple. We're going to give this unreacted nitrogen something it can't refuse. So instead of going ahead and deprotecting immediately, I've been writing alanine so much. Acetic anhydride or TFA anhydride. So both of these are anhydrides. They're very hot electrophiles. Nitrogen, the amino group, is going to react with them. And it's no longer going to be an amino group. It's now going to be an N-acetyl group or an N-trifluoroacetyl group. So just to write that down because it's not going to make any sense. TFA anhydride will lead to... The nice thing about the TFA anhydride is because it's really, really electrophilic. And the other nice thing about it is that the fluorinated head group on it makes it a lot easier to separate from everything else that doesn't have all those fluorines. Just gives it kind of a very different chemistry. So now, of course, that's no longer a free amine. And so it's not going to couple to your next amino acid. You've taken it out of contention. So instead of having to separate 29 amino acids from 30 amino acids, you're now going to separate 30 amino acids from like a 2 amino acid peptide if this went on, where it's going on here. And that's easy because 2 amino acids is very small. It's going to behave very differently from a 30 amino acid peptide. You're going to get in a very different place on your HPLC. So capping is really useful when you think you have a tough coupling. Okay, so let's say you've done your synthesis. And you've got 30 amino acids on here. So how does this cleave? Well, what we're going to do, how do we get it off the bead? So we've made a bead. We have our peptide on the bead. We don't want our peptide on the bead anymore. We're ready to take it off because we're done our synthesis. What we can do is we treat this with acid. In this case, TFA. So how does this work? Well, if we remember what that green bead was, that was wine resin. And when we treat this with acid, we're going to protonate that oxygen. So since I drew TFA up there, I'm actually just going to put that over there. Now, is that the only place it's going to protonate? Fuck no. It'll protonate all over the peptide and things, but just nothing really productive is going to happen. Like, peptides are actually, it's kind of amazing. Proteins are really resistant to strong acid and strong base. You will denature them because you will break up their three-dimensional structure, mostly because you'll break up hydrogen bond interactions and things. But you won't actually break a lot of chemical bonds in proteins. Like, again, if you take a look at the functionalities that are present, I always think amino acids are the most boring functionalities out there. We've got some amines, we've got some alcohols, we've got some carboxylic acids. We don't have a whole lot else, like a few nitrogen heterocycles. And yet, together, these weak bases and weak acids and shitty nucleophiles are able to do basically any kind of chemistry. Like, we were seeing them make glycosidic bonds, just these weak systems. And it's all because of the way proteins are shaped, right? And the way the environment's shaped. And it's just, I hate them so much. They're so much better than anything I'll ever be able to do, and it just depresses the crap out of me. Anyways, they're really, really resilient to everything because they just don't react with very much. So we're going to break a carbon-oxygen bond. Why are we going to do that? Well, that's a really stable carbocation that's going to be generated next to it. It only ever has to happen once. So this is chemistry actually very close to my heart. It's close to Susanna's heart too. So we follow what just happened here. We're relying on the fact that we can make a para-orthoquinomethyde. So you have a really good leaving group. And a little bit of water acts as the nucleophile to restore aromaticity. These kinds of hydroxybenzyl alcohols or hydroxyphenols. Hydroxybenzyl alcohols is stupid. Hydroxymethylphenol. I'm just going to write that down. Plug in before this dies. are inherently unstable if they got to protect a leaving group on that oxygen, because they can easily make those orthoquinomethides kick out whatever is attached to that oxygen, kick out the oxygen or anything attached to this carbon. It's gone. You can't put a bromine on there. You can't put an iodine on there. The molecule doesn't last any length of time. It just loses it immediately. And so in this case, our leaving group is our entire peptide. So we just had our peptide fall off. So this is called, resin cleavage. So we can build this entire thing stepwise through sequential deprotections, couplings. We can use double couplings. If we have a tricky coupling that we don't think is going to completion, we can cap it. Once we've made the entire thing, we do this cleavage. Now, 30 amino acids is getting near the limit of where you generally want to make a peptide on solid phase. There's some ways around it, but the problem is, let's just think about what this surface looks like. So you have a bead. Hydrophobic. So your peptide starts probably inside a cavity in the bead. So there's like a growing peptide chain. There's your little peptide. And out here you've got solvent. Your solvent, generally we like using DMF as solvent. We've seen it a lot for this. It's not arbitrary. The reason why we like DMF so much is, look at that amide bond. So that can now, so first of all, it doesn't have an acidic NH on it, so it's not going to do some chemistry. If there is an NH there, sometimes that could be a little bit weird. It might do something. We don't want that. But we have a really good hydrogen bond acceptor in an amide, and it's an amide, and the peptides have amides, and like dissolves like, so amides dissolve peptides. Great for peptides. Now, generally when we think about peptides, I kind of think of them as hydrophilic generally. I just do, and I'm wrong. They're not. Most peptides are relatively hydrophobic. But just in my mind, I'm always thinking they're hydrophilic because they're a biomolecule and they're soluble in water, so they must be hydrophilic. But the other thing we know about peptides is they're, as I think Kirsten told us at the beginning of the whole section on this, is that they're subunits of proteins. And proteins adopt secondary structure. So, why don't peptides adopt secondary structure? Well, if you're lucky, your peptide is too short to adopt secondary structure. The problem is about 25 amino acids. Peptides are adopting secondary structure. And why is this a problem? It's not a problem that the secondary structure they adopt would be an alpha helix. Because then what you would have is, you'd have a helix and you'd be fine. The problem is that alpha helices aren't generally very stable if the ends aren't continuing on both sides. You don't normally ever have an isolated alpha helix. There are some exceptions with really specific sequences, but it's not the general thing that often happens. What often happens is we get the other secondary structure, which is a beta sheet. And if you remember what a beta sheet does is it goes out, it does a beta turn, then it comes back. Peptide folds back on itself. Therefore, sterics. Because now what's happening is this thing is basically burying back into the bead. And now you have all these steric issues because you can't get stuff in there because it's crowded because it's up against the bead and it's folded on the other part of the peptide. And now your nitrogen is making hydrogen bonds with the backbone. And it's just, oh God, it's a nightmare. So this really takes over about 25 to 30 amino acids. Okay? But people can make them longer, so we cheat. Mess with the solvent. So what we need to do is we need to give the peptide a better reason, something better than itself to interact with. And that's what we do. So swap DMF for NMP. This is N-methylprolenone. I'm just going to draw it because if you want, you can look up NMP plus solvent, and that will get you the right structure and the name. But the name doesn't matter. Again, we have an amide bond. But now, it's a lot like DMF. It's like what happens is if you take DMF and it has a love child with ethene, because we just have like DMF and we've attached ethene and we've closed the ring. But now what we've done is we've added some steric strain to this whole thing. We've added some steric size. And so now this guy takes up a bit more space. So when it binds in to your peptide, it doesn't really allow the peptide to fold back around because it's got this freaking NMP solvent thing that's taking up space. My cat is chewing on all my cables. Come on, Zoe, I'm sure you're gonna... No, okay. She does not want to come up off the floor. She wants to chew on cables. So what this does is disrupts beta sheets. Allows for longer peptides. So that's good. I think the record is about 83 amino acids. In good yield. I think some bastard has actually gone and done like 200 amino acids or something to make a peptide, but the yield was really shit. But about 83 amino acids in good yield, and by good I mean greater than about 30%. It was a very good sequence. There were no tricky couplings. Again, your yields can drop off massively if suddenly you have some tricky couplings in there. It behaved itself and it didn't fold back on itself. There's some examples of like 7 amino acid peptides that are really, really hard to make. And people who make these kind of peptides on a regular basis know that they're hard to make, and they sort of show how good their protocol is because they can make this better. but this allows us to make longer ones. Okay. I think I'm going to leave it there for today. What I want to take up next class is we're going to talk about basically post-translational modifications. So if we're doing biology, a post-translational modification is anything that the peptide or protein does after it comes off the ribosome. We've made the peptide or protein on the ribosome, and now it does stuff like glycosylations, phosphorylations, oxidations, side disulfide bond formations. We can do something similar chemically. So we can have made the entire peptide on a bead, and then we can do chemistry before we take it off the bead. The two examples I really, really want to talk about are, one is preparing things for bioconjugation and glycosylation, and the second one is disulfide bond formation and peptide cyclization. These are, I think they're becoming more and more important as technologies on peptide synthesis. So we're starting to see more and more cyclic peptides, and we'll talk briefly about why cyclic peptides are starting to basically take over the world. Hi. And Zoe's going to join me for that lecture too, probably. But I think that's where I want to go with this next class. And I'm just thinking I just don't have enough time to really get into anything in 7 minutes, so now I'm going to try. So I posted the last two assignments. They're up. Exams based on them. We're going to cover that material. I think because I dropped some of the stuff I really love, I'm just going to have to double check and make sure that I'm not. There might be a question or two where I say don't do this question because we didn't cover that this year. I think stuff with C glycosides and carbon sugars we just didn't cover, and that breaks my little heart. But we're a little bit behind. And I always feel the end of this class gets squished. The end of the class is probably more important than my pet little thing. Yeah. I think Kirsten and Ashley, you guys owe me something for the presentation very soon, if you haven't already owed it to me and you're late.
Yeah, we're just I just sent my part of the bibliography over to Ashley, so hopefully she sends it tonight, but I can probably get it to you tonight.
Technically, when is it due?
Today.
Okay. Okay, good. If it's a little late, that's okay.
Okay, thank you.
No penalty. And I know that the grad students got scooped. Like, they got scooped, a few years ago, but they got scooped. So they're working back for a new subject.
Yeah, it's been a struggle. We're still brainstorming, I think. Oh, Samra just joined.
Yeah.
Oh, I actually joined late. I think there's daytime saving or something. I turned out to have